So it's really difficult to, I think, to define what is a shock. And so we have to sort of get a concept and a feeling for the kinds of things that might be called shock, as opposed to those that aren't. And these three are three examples of shock, and I think they all three show the same kind of thing that I think of as shock. They start off with not much happening, then something happens, and they end up with not much happening. And it doesn't matter whether it's milliseconds or seconds, or actually 8 seconds is even short for an earthquake, because they can go on a lot longer than that, can't they? Especially if you're not near the epicenter. I don't think the actual time comes in. To me, a shock basically says nothing's happening, then we get a mechanical, because we're thinking mechanical shock, some sort of mechanical excitation, which causes a response, and then it stabilizes. So transient to me is sort of off, on, off. I think that's the sort of measure of a shock. Now, in a specific industry, you're going to lock into very tight and say that's a shock, and this isn't. For example, an elastic impact like this. When we get elastic impacts, what kind of thing, any idea gives us this, like almost a half sign with elastic impact? Any ideas?
Shaker? Or a shock machine?
No, not a shaker, and you'll see why soon. Surprisingly, not a shaker. But things that you've talked about.
Machine?
Which one?
Drop
The drop tower, yeah. If I take something like this, let go. Oh, that's very, very, sorry. That's very close to a half sine wave pulse. Have you ever done half sine wave pulsing on your shock machines?
I have, but not in the one of.
You have not?
I have.
No, you haven't. No. Don't tell the guy with the mass matrix that if he says go do a half sine shock on a shock machine, then the answer is no. You can do it on a drop test, but you cannot do it on a shaker table. And I'll show you why.
Oh, I see what you're saying. Yeah, because of the pre and post is not really.
Yeah, you have to do stuff to it.
Right,
and we'll see why and how we do it. Yeah, right. That's the other one. Let's do a half sine shock pulse. Yeah, right. Half sine shock pulse like. Here, so we got this nice half sine elastic. That's for anything where it's like hitting spring, rubber. This is fairly springy like. That will give us something like that. Very short-lived. This guy here is a in-air drop of an explosive. Yeah. So here, the pressure can't go negative. Gauge pressure could go -1 atmosphere. Absolute pressure can't. But essentially, we're looking at hundreds of psi. So essentially, the pressure can't go negative. So it's all one-sided, and that to me is a good shock. Who's happy for shock? Earthquakes, we talked about those quite a bit. We'll talk a bit more about the PNS waves and things like that. Torpedo entry. You drop torpedoes into water, something happens as they hit the water, and then get a little wind down before they go off and do their business. That was always a big one for a while. So I think it's very difficult to just say, this is the word. We think rapid, but that's kind of, is 20 seconds rapid if we're thinking of an earthquake? It seems like a long time if you sat there. But in terms of the structure, it's actually quite quick. So it's difficult to define. What about a car going over a section of rough road? It's going to depend on the speed of the automobile. Yeah, that's going to change things. So what we'll find is that at slow speed, I wouldn't talk about hitting a pothole at slow speed to be a shock event. But if it hits at high speed, I would. So So we've got other things going on there. So here's some causes. Got any others? Sure you have. Earthquakes. That's a big one. Lots of. You'll see the SRS was developed for earthquakes. Handling in manufacture. Very often, the final product that comes off a manufacturing line can be quite robust, but the components on the way through can be very delicate. Yeah, you got a circuit board with lots of pieces on, and you pick it up like that, you've just broken it. Once it's embedded in with all the right posts and captivating devices and things, it's quite robust. What about eggs? You put eggs into a box, you can shake them around a bit, and oh yeah, you can break them, but they're fairly safe. But in the manufacturing plant, well, it's not mean manufacturing, but the packaging plant, they've got to take these delicate eggs and somehow get them in the box. And so we can get issues there with packages being dropped and moved and things like that. Potholes, clearly. Talked a little bit about that already. We get things like in the rail industry, that sent stuff by rail. We had freight car humping. What's that?
Very long shock.
What causes freight car humping? What is freight car humping?
Coupling?
Yeah. It's not how we make little toy trains.
Yeah, those tend to be pretty long duration.
It's when they come up and go on the back end, and you get this all the way down the train and back again. And my grandmother, she's been dead quite a long time, but when I was a kid, as a teenager, she used to live across the river on the northeast coast of England from a very big railway shunting area with all the steam engines. And I used to love sitting up in her top of her house, looking out the window, and you'd see across, and you'd hear this, and all the steam comes out, and then you'd hear that bang, and you'd see that shuffle go shooting down all the carriages. And that could be more serious than actually the shock and vibration just from shipping. Water wave slam. That's a big one. You get to see. Have any of you been at sea in rough weather? No, thanks. Ex-Navy. Spent too much time at sea and throwing up as well. All sailors are thrown up. If they tell you they've never thrown up, then they're not really good sailors, because every sailor I've seen, even experienced, well experienced sailors, still thrown up at sea. But there's two different kinds of slamming that we can get there. The one is where we call it shipping green, and that's, you've probably seen pictures where a ship plows into a deep wave and disappears underwater. Basically becomes a submarine for a short while. If you're up on the bridge of those ships looking out there, what you see is this wall of water just slowly come at you. And then you get this bang, as these tons of water hit the front of the deckwork. And that sends a violent shock through the ship. And then hopefully the ship comes up ready to plow onto the next one. And then the other one is the ship literally just riding out of the waves and slamming down. And again, you get this massive shuddering going on inside the ship. And that is a serious issue we have to consider, because you can't just suddenly avoid bad weather if you hit it. In the air industry, landing. It's like a graceful crash landing, I guess, isn't it? Every landing's a crash, only some are more successful than others. If you're firing up an aircraft carrier, and the catapulting itself is a major shock to the system as it goes off. By the way, your aircraft are probably not hardened for carrier landing, are they? No, carriers. No, but you don't harden them either, do you, for it? No. If you think of aircraft that both the Army and the Navy have got, supposedly the same aircraft, they're really not. Because the spine of the ones for the aircraft carriers are significantly strengthened. Because A, they need to be pulled apart by the catapult launcher, and B, they're then going to crash land. Literally, it's almost like a crash landing, and tailhull can suddenly be jerked to a stop. And if you were to take an Army variant and try and land it on the aircraft carrier, just tear it apart. Just one-shot landing, you're done. But catapulting is very severe. Parachute opening. Parachuting people or stores, when the parachute opens, all of a sudden you get this big shock going. And when it hits the ground, another shock. Blowing stuff up is always fun. So lots of examples there. Think of your own favorite. Got any other favorites that aren't on the list? It actually covers quite a lot of things, isn't it? Yes, you got any others?
Crashes.
Yeah. Accidental crashes. Hopefully. Yeah, unless you're German, was it Eurowings or whatever it was. Anyway, let's look. What are the effects of shock? We're going to stop at the end of the screen now. I'm going to show you one movie then, I think, which is worth doing. What are the effects of shock? Well, humans, discomfort or injury. Yeah. We have a 100% Navy shock, and that 100% Navy shock is defined as the shock that if you were to stand with your knees braced, you wouldn't do this on shipping birds, but if you were to stand with your knees braced, stand upright, and you get a 100% Navy shock come up underneath, it's just enough to put your knees into your hips. That's one of our standards. I would call that discomfort or injury, or death. Yeah? So it can be quite serious kind of shock like that. Malfunction, temporary. what about malfunction temporary? Is that a failure or not?
Can be.
Go on, then, Rich.
It depends if it's mission critical and what that is. That transient failure is part of a fire control system and it releases munitions. Then
Exactly. Yeah. One of the examples I like to talk about here is if you take a laptop, you haven't got any, so I can't demonstrate it. You're not using mine for that. If you let go of the laptop like that, what happens? Which piece is likely to break?
the old hard
Not
drives.
anymore.
Not anymore. No.
Right, because you know about it, John?
Solid state.
Oh no, I was thinking just spinning disk still.
Yeah.
Spinning disk. In the good old days, as in more than 10 years ago, I guess, it used to be that the hard drive was the most one of the most sensitive pieces, because if you got the disk spinning and the head's inside, when it hit, the heads all crashed and banged down and damaged the surface, damaged the heads, and then damaged. All of a sudden, they managed to make them much more shock tolerant. And the way they did it was to put an accelerometer into the drive. And now, that little accelerometer just sits there, and if it detects free fall, it goes, uh-oh, stop. And it doesn't stop the drive, it retracts the heads. Because you can't stop the drive. So it just leaves the drive spinning, it retracts the heads. Boom. Okay, back to work. On you go. And I love your description of the fire control system, because if it was critical for you to spool data either on or off that hard drive during the free fall, you can't do it. So all of a sudden, we've got this temporary malfunction. You can't read anything off that hard drive until it's hit and stabilized. But things still keep on working. So this one here, temporary malfunction, that can be critical or not critical. And if it's not critical, we don't care about it. But it can be critical. Something like a power switch. If we drop or it hits a instrumentation cabinet, and the switch throws, you probably test those from time to time. Instrumentation cabinets.
I have in the past, not in the current position. I mean,
All right, but you've seen a test.
Yeah.
If the switch, sorry.
So you're supposed to be silent on the sub and you drop a wrench.
Yeah, right. But there, if the switch throws and turns the power off, then is that a temporary or permanent malfunction? Well, if it doesn't really matter, you just go zzz, everything goes back to life. It's a temporary malfunction, isn't it? But if, again, part of the fire control system disintegrates. And that's why we think about things like road switches instead of linear switches for shock environments, those kinds of things, so that they're less likely to throw. You get loosened parts, bent stuff, of course, the fun of life, breaking things, and all that lot. But I can only think of 2 remedies. Do you think of any more? Can we somehow reduce the energy going into the thing, or can we reduce its sensitivity to that input? This is looking at the design of the component itself, and making it shock tolerant, changing those switches to rotary from linear, stronger components, whereas like to get broken, thicker circuit boards, putting that to potting the circuit boards so that the components don't rattle. This one is saying, can we put in shock absorbers, packaging with space for shock? But really, that's all we can do. There's nothing else. Because we can't usually control the shock. FedEx drops your box. FedEx drops your box. That's it. Done. If the enemy blows up a torpedo near you, that shock's coming in, and all you can do is either reduce the effect on the system by making them stronger, more shock tolerant, or somehow doing something with that energy to stop that energy. That keyword we started with this morning, energy. Okay. Now, what I'd like to do is to just have a look at, if I can find it. This is a movie that Mark and I made. We're going to be looking at the vibration of a beam. On this situation here, we have an electrodynamic exciter, which is driving this beam at this point in the middle. We've got 2 beams, one on the left and one on the right. They're both the same, and I put 2 beams on here so that it puts the center of gravity directly over the drive point. If I tried to develop just one beam on one side, the center of gravity would be over here somewhere, and when I drive it, the resulting torque would have given us a motion which is not easy to see and is not a cantilever beam. So we're going to be driving up and down in the middle,
and we'll see if we can find some resonances, and we'll look for the mode shapes. I'm driving the beam at 13 Hertz, and we can see that we're getting quite a large motion, but we're not quite at resonance. Let me slowly increase the frequency, and as I slowly increase the frequency, we see the amplitude of motion get bigger and bigger, until we're at full resonance. And this is about 13.5 to 14 Hertz. And we can see some quite large motion. Let's try and see what that looks like with a strobe light. So the beam is vibrating at about 14 Hertz. It's at its fundamental natural frequency. And I have the strobe flashing at 13 Hertz approximately. And so we can see the beam apparently moving at 1 Hertz. So we can see the mode shape there. The mode shape is essentially zero displacement in the middle, zero slope. Remember, we're looking at two cantilevers, one on the left, one on the right. So we're expecting to see the same thing on each side. I'm now moving up to the second natural frequency. I'm driving the beam at 77 Hertz, which is just below the second natural frequency. And if I slowly increase the frequency, we'll see the beam motion get larger and larger. It gets into resonance. Now we have some large motion resonance, and there we have the peak motion. There's some interesting things happening now. The middle, remember, is still expected to be zero displacement and zero slope for the boundary conditions, but now we have something happening right here. We can see a node, a point of no displacement. The beam here is moving up and down as a sine wave. The beam here is moving up and down as a sine wave. But at this point here, we have no displacement. It's called a node. And we will see that this part of the beam is out of phase with this part of the beam. Let's look at that with the strobe light. And just like before, I'll set the strobe slightly off 84 Hertz so we can see with the aliasing effect, we can see the beam moving slowly. Here we are showing the second natural frequency with the strobe light, and we can see the node point is about here somewhere, and this part of the beam is out of phase with this part of the beam. The beam is still shaking just over 80 Hertz at its second natural frequency. We've just slowed the motion down by looking at the strobe light. I've now moved the frequency of excitation up to 234 Hertz. This is now the next natural frequency, the third natural frequency. If we look at the mode shape, we can see no motion here. At this point here, we've got large motion. We have a node here, no displacement, more displacement here, a second node at this point, and then motion at the end. And so if we would look at the phase, which we'll do with the strobe light in a moment, we'll see that at this point, the phase is 180 degrees from this point, and the phase is another 180 degrees back to this point. So the tip and this point will be in phase, and the middle will be out of phase. That is a characteristic of all nodes, that if we transition from one side of a node to the other side of the node, we will see a 180 degrees phase shift. Here is the beam at its third natural frequency of 233 Hertz. And again, I've got the stroboscope just a little off that frequency so that we can see the apparent motion going on. For a structure like this, a beam which is fixed at one point, we can decide which natural frequency it is by counting the number of nodes. In this case, we have one here, two nodes, and that becomes the third natural frequency. That rule applies for any structure which is fixed, but if we have a free structure, we have a different rule. But essentially, the higher the frequency, the more the nodes. I've now increased the frequency to the fourth natural frequency at 454 to 455 Hertz. and it's difficult for us to see the beam moving. Let me increase the power to the shaker and see if we can see it moving. We can just make out a little bit of motion. Here it is at low level, and there it is at high level. We can just see some motion. We can also hear a little harmonic distortion in the amplifier because we're not getting the pure sine wave. Let me just ease that down a little so we reduce that harmonic distortion. It's difficult to see the motion because it is so small. I can, though, find nodes. There's one node here. Second node here. And a third node there. 3 nodes, therefore the 4th natural frequency. Let's see what that looks like with a strobe light. I've now increased the frequency up to 752 to 753 Hertz, and we are now driving the beam at the 5th natural frequency. The motion's got quite small, although we can hear it, we can't see it. The displacement has gone down as we increased in frequency, while the acceleration went up. If I increase the power to the shaker, like I did last time, I can hear some harmonic distortion, but I still can't get enough displacement for us to be able to see it clearly. But I can still find where the nodes are. Let's see if we can find them. There's 1. There's 2. The 3rd one. And the 4th one. 4 nodes, and therefore the 5th natural frequency. Let's look at a different way that we can find the node lines. What we're going to do is we're going to put some salt onto the beam, sprinkle it along the beam, and then as I turn the power back onto the shaker, we're hoping to see the salt move away from the points that are moving and settle where the node lines are. Here we go. And so there are node lines very clearly displayed. 1, 2, 3, 4. The 5th natural frequency. I've now increased the frequency to 2,691 Hertz, and from the noise coming off the beam, we can tell we're near a resonance again. But the displacements are very small and we can't see them. Let's try putting some salt on and see what happens. Let's put the energy back onto the shaker. And we can see 1, 2, 3, 4, 5, 6, 7, 8 nodes, therefore the 9th natural frequency. Let's see if we can find another one. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 node lines. Now the 11th natural frequency. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, the 15th natural frequency for my cantilever beam. Now we're driving the beam at 12.6 kilohertz. Let's apply the power to the shaker, see if we can find the nodal behavior. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It looks like the 16th natural frequency, but now we're getting to such short wavelengths that we're starting to get this kind of behavior here. And look, there's a little node running up the middle. We're actually starting to see this beam act more like a plate. So let's look at some plate modes. We saw on the last beam mode that we were starting to get node lines that were not straight across the beam, but starting to move along the length of the beam. That's because the beam was starting to act more like a plate. So what we're shaking now is a small square plate. I'm driving it right now at 62 Hertz. I put the salt on, and I turn the power onto the shaker. What we're seeing now, instead of getting node points, we're now getting node lines. And in this particular mode, there is a node line running across here, and another node line running across here. But what we're seeing is that actually it looks like a curved node just because of the way the two nodes are pulling together. Let's put a little more salt on, and we'll look for that shape pattern to develop again. So at first, it looks like we're getting curved lines in here, but really we can see quite nicely now the two node lines running at diagonals across this square plate. And we can see two node lines, one across here and one across here. What's happening is this plate is now acting like a beam that is bending, and these are the node lines coming across here. Remember that every time we cross a node line, we change phase, and so if this part of the structure is going up, all of this central part is going down, and all of this part is coming up as it goes through the sine wave. There we see. They're not perfect straight lines, slight curves to them, but they are acting more like a beam than a plate. Let's see if we can find another resonance. What we've found now is we have multiple node lines. Two node lines going across here, and in the other direction, two node lines going across here and here. A little bit of curling in the corners. This is a classic mode for a plate where we see in phase, out of phase, in phase, in phase, out of phase, in phase, in phase, out of phase, in phase, all across the plate. A node line across here, a node line here, a node there, and a node there. I'm now at 1557 Hertz. As we increase the frequency, the mode shapes become increasingly complex, and we can see the behavior going on here. It's a symmetric plate, it's square, and so we expect to see a symmetric mode shape. Remember, these are the node lines, the lines of node displacement, and as we transition from one side of a node line to the other, we always see a 180 degrees change in phase. I've now increased the frequency to 4.6 kilohertz, and we can see quite a complicated node behavior. It is still close to symmetric, but we've started to lose a little bit of the perfect symmetry we saw before. That's very common with structures because the structure itself is not exactly symmetric, it's not being driven at exactly the middle, and those small changes will become more noticeable at the higher resonances.